We are going to talk about orchestrating the microservices with GraphQL, but we are not going to talk about the GraphQL, how to set up the server, etc. This is not the talk about that. Before we start, let me just introduce a little bit myself. So I am a principal engineer at the Intuit, at the Intuit Developers Group. I've been working on the next generation of the Intuit platform API and SDK for it. I am a product owner and the tech lead on the SDK and on the platform application service. That's what stands for PaaS. I also was contributing to the current API. I was developing, I was an author of the simple query language, that's a language used for query the services for the data, which is based on SQL. And also I am the contributor to the GraphQL Java library, open source project maintained by the community. So, what we are going to talk about? We are going to talk about what does it mean to orchestrate the request. And as an example of the request that needs to be orchestrated, we'll be using GraphQL as the emerging popular protocol, but it doesn't have to be limited only to GraphQL. The problem with orchestration will be common to any protocol you can choose. So we'll talk about the what does it mean to do the orchestration. We will also talk about relationships between objects. We will talk about the role of the data resolvers or data fetchers, depending on what library you are using. What are the problems where the current approaches that are popular in the GraphQL community stop working very well. And also, we will talk a little bit about what kind of solution we have at Intuit to avoid or to solve these problems. Just also to mention that we are one of the earliest adopters of the GraphQL, since it was open spec'd by Facebook in 2015. We've been already three years in that game, so I think that our experience is also relevant here. So let's consider, let's say the problem. So let's consider the API gateway that is connected to a set of microservices to talk to. I will be using the financial domain, but that should not be a matter to use any other domains as well. So we have, for instance, a bunch of services, like the service that provides company data, the service that provides contact data, invoices, accounting engine, and the items engine. So these are just most important, most common services or data types that belong to the financial domain. And we have a bunch of clients who use the API gateway to access the resources behind it. The role of API gateway is to simplify access to the various microservices and various kind of data that company has. So unify the API between them, and also provide one of the important values, the location transparency. So the client doesn't have to know where the data is coming from. The client just needs to send a request saying, give me that data, and boom, the system will respond to that request. And also it serves for the purpose of optimizing the traffic, because all the necessary communications happen behind the gateway. There will be minimum number of the requests over the slow network, and there will be as many as we need requests behind that on the private, fast private network. So let's consider a GraphQL request that comes to the system. The GraphQL request, again, applicable to this domain, looks like that the client wants for the company with ID 1, 2, 3, 4, 5 fetch invoices. Actually, the first one of the invoices that belong to that company, and it wants to fetch that invoice or those invoices with a customer that associated with that. So that's a relatively huge request. If it was a, let's say, just plain REST communication, then it would be translated to a series of calls, go and fetch the invoice for this particular company, then go and fetch a customer for that particular invoice, and then the client would need to join them together. What happens here is after the API gateway receives this request, it decomposes the request and it organizes the calls to the downstream microservices, asking them for the particular data they can provide. Then it joins everything together and sends that back to the client in the form that shown here. So the client receives back the object that contains the invoice and the customer that associated with the invoice. So that's the role of orchestration. Now, let's take a look again at the request that is coming to the system. And what the GraphQL engine does, it basically builds an abstract syntax tree from that request. The color coding here is that the scalar fields are represented as the red boxes. Those are atomic data elements that live in one particular place. Green elements, they represent objects, and these objects are stored in multiple systems. The cyan elements, those are arguments like IDs and IDs of the objects requested, or the pagination parameters, etc. So among these fields, or among these nodes in this AST, there are three important nodes, which are the field node for the company, field node for the invoices, and field node for the contact. Why they are important? Because they represent objects served in different systems, in different microservices. So we call them relational objects. And the field company means that go ahead and fetch some company data from the company service. The field invoices means the same. Go ahead and fetch invoice from the invoice service. And field contact means go ahead and fetch contacts from the contact service. And then also it implies that after the company is fetched, then we know the ID of the company. We can go ahead and fetch invoices that belong to the company. The same is after the invoice is fetched. Invoice contains ID of the contact, and therefore we can go ahead and fetch the contacts from the contact service. If you look at the same process from the perspective of what the standard engine is doing, the standard engine, let's say standard reference, Facebook or Apollo engine, they associate, and the GraphQL Java library that is basically a port of the reference implementation to Java, they associate with every field a special object called resolver or data fetcher. And when the query is being executed, basically when the fields are being evaluated, the corresponding data fetcher is being called, or corresponding resolver is being called. The resolver does the things, goes and queries the data from its service, and then this data is provided to the engine, and engine does all the joins. That's what the normal standard execution path of the GraphQL query looks like. Now, where it is falling short? Let's slightly modify the query that was shown on the previous slide. And let's add a parameter to fetch invoices. Let's not only fetch the first invoice that belongs to the company, but let's also specify that a criteria, what kind of invoice we want to fetch. And in this particular case, what is interesting is to specify a criteria to fetch an invoice by the attribute of the associated contact, not by the attribute of invoice itself, contact. And this is important. I provided this example in the simple query language, which is, as I mentioned to you, SQL-like. This is not standard. GraphQL spec does not say anything about criteria. So that means that you can, when you define your schema in GraphQL, you can always add arguments that best represent your domain. And in our case, we chose to represent arguments, to have the arguments that could specify criteria in that simple query. There are other popular ideas. By the way, the idea of specifying expressions as arguments, it is flying around in the community, and who knows, maybe it will be adopted. At least we will be supporting that as well. And there is another API which you might be familiar with. It is called Prisma API. They define for every queryable object the input type, called filter input type, that is useful in that sense that if you construct your query with the console like GraphQL that can do the introspection of the query, you will have all the IDE support or all the console support on with predictions on what kind of filters you can specify. But that is not very much relevant here. What is relevant here is this: if we follow the standard execution path of the GraphQL request, just like we followed it before, what will end up happening is that without extra care, the query for the invoices will go to the invoice resolver, and that resolver has only two options: either to go ahead and try to query invoice by customer attributes that invoice service doesn't have access to anyways, or to try to orchestrate that that criteria query on its own. And as far as we understand, the attempt to orchestrate the criteria query across multiple services outside of the GraphQL engine basically defeats the purpose of the GraphQL engine itself, because GraphQL engine is supposed to normalize the data resolver. They will ask only for the data that is required, and then the engine will join everything together. In this case, it is either the engine cannot orchestrate this itself, and therefore resolver has to do some extra work. And we feel that this is not necessary. So, why it is not necessary? You can treat each microservice in the system as the table, and of the type that microservice that microservice serves. Company microservice serves company objects, and contact microservice serves contact objects, and the invoice microservice serves the invoices. And if you also look, the invoices have the reference to the company. That's how we are able to find the invoices that belong to that company, as well as invoice has the ID of the contact. That's how we can find the contacts that belong to a particular invoice. And that's what helps us to do the criteria search. Because in this case, all we have to do is just to calculate Cartesian products between 3 data sets. We need to fetch companies with a particular ID. We need to fetch the contacts with a particular attribute, and then find the Cartesian product in order to calculate what invoice we need to fetch, and then go ahead and fetch invoice. And then merge everything, join everything together and send the result back. So I will probably skip some of the slides as not that important. I can only show another problem similar to that, is mutation problem. What if I need to create an invoice with a contact? The same thing. The GraphQL engine does not decompose the input types. It treats them as atomic types, and therefore responsibility of orchestrating mutations, cascaded mutations, lies on the shoulders of the resolver. So, what would be the solution? The solution is actually pretty simple. If you look at these 2 problems from the perspective of who depends on what, you might come to the idea that managing these calls with dependency graph would be helpful, and that's what we do. So for the query for the first example with the query, we basically build a dependency graph where each node in the graph represents a relationship. And in this case, we have the company service or company node that doesn't depend on anything. We have the invoices that depend on company and the contact that doesn't depend on anything else. And that helps us to basically, because this is the dependency graph, to calculate the transitive dependency closure, or to just walk these dependencies in their natural order and calculate which queries we need to send in what order. And what that ends up having, we are able to select immediately two queries that we can, by the way, run in parallel. The query to company, to fetch the company with a particular ID, and fetch the customer with a particular criteria. And then after we receive those, we can go ahead and fetch the invoice because we have all the criteria to find the invoice. And then after we resolve the invoice, we can actually produce a result, which is the join happens in the result node with number 1. Similarly, the cascaded mutations could be solved absolutely the same way with the dependency graph. It's just the way how you build the dependency graph. In this particular case, in order to create a new invoice, we need to have customer ID, which means that invoice depends on the customer. Therefore, we build dependency graph in such a way that the invoice node depends on the customer. But after we build the dependency graph, we traverse that graph or calculate the closure the same way as we did that for the query, and that produces us just the mutation. And we feel good about it. We are about to deploy the combined service that does not depend on the GraphQL engine to orchestrate. It only uses the GraphQL front end to parse the request and some utility methods how to map input types on the target language. But the orchestration is completely bypassed. It is based on the dependency graph. The good thing about it is that with the same way we can orchestrate not only GraphQL requests, but also REST requests, gRPC requests, any sort of request that might come to our attention in the future. And that's basically it. Thank you very much for listening.
If you want to take 2 questions.
Yeah, sure. Questions? Yeah.
What are you actually using to build the dependency graph?
We implemented dependency graph our own. We created dependency graph ourselves, and we just build a mechanism that builds dependency graph for each of the particular keys, for the queries and for the mutations. And then we have the metadata that we derive from the objects by introspecting their schemas, and based on the metadata, we make decisions what kind of relationships objects have, because we can recognize that, let's say, parent and child might be in associated relationship where the parent depends on the child, or vice versa, for instance, in composition relationship where child depends on the parent. Other questions? I think we're done. Thank you very much.